Okay, so now we're at the culmination of this unit, which is hypothesis testing for the difference of population proportions. So suppose we may want to compare the two proportions from separate populations to see if there's evidence that they are indeed the same. We assume that they are the same and then proceed to use a significance test to see if we have sufficient evidence to support or not support the initial claim that the proportions are equal. So back when we did a one sample, we assumed that we knew the population parameters because we assumed we knew the true proportion. However, now we don't assume that we know the true proportions. Instead, what we assume is that they are indeed the same. So we're trying to see if this proportion characteristic from two separate populations is equal or if there is some difference, and then that difference is noted in the alternative hypothesis. So we're actually going to take a look at the 2019 question 4, which is a very fun one, but I do want to draw your attention here to the test statistic. So notice this one looks a little bit wonky. This p hat of c is just what we call the pooled proportion. So you can see that the numerator measures the successes from both populations divided by the total sample size of the populations. And we do this because we assume they're equal. So if they're equal, we should be able to combine them since they are the same. Some logic like that, but the rest of the process still follows out. So let's take a look here. Tumbleweed, commonly found in the western U.S., is the dried structure of certain plants that are blown by the wind. Kochia, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. Scientists are concerned that kochia plants are becoming resistant to the most commonly used herbicide, which I believe is glyphosate. I'm just going to call it Herb-G for now. In 2014, 19.7% of 61 randomly selected kochia plants were resistant, and in 2017, 38.5% of 52 randomly selected kochia plants were resistant to this herbicide. Do the data provide convincing statistical evidence at the level of alpha equals to 0.05 that there has been an increase in the proportion of kochia plants resistant to glyphosate? So let's start with our state part of the process, which is going to be our parameter and our set of hypotheses. So we have two parameters here that we're comparing, and the first one is going to be P14, which is the true population proportion of kochia plants resistant to glyphosate. You know what, I'm just going to shorthand, sorry, to Herb-G in 2014, whereas P17 would be the true population proportion of kochia plants resistant to Herb-G in 2017. Now, granted, you'll have the paper in front of you, so you can be a better copier than Mr. Pinto is being. And we need a set of hypotheses here. And the first one is that we believe that these two proportions are equal, right? We believe there's actually not a difference in these proportions, but instead that they are assumed to be equal. There's no difference. But in reality, we believe there might be statistical evidence that the proportion in 2017 is greater than the proportion in 2014. And we are going to do this with an alpha equal to 0.05. So that's our state part of the process. Next up, we need to check the assumptions and name the test. So keep in mind here that we do have to, we have 4 assumptions that we're checking. So with the assumptions, the first one is that we randomly selected, how many plants was it? Sorry, y'all, kind of cheating here. The first one was that we randomly selected 61 plants in 19.7 of those, and then in 2017 we selected 52 and 38.5 of those. Okay, and y'all, I work these problems live, so you can see that, like, hey, it takes a little bit of effort even for teachers to do these. So let's see if, oh, and you know what, it's not going to let me edit this one now. I just love hybrid learning, but alas, here we are. All right, back in action here. And now I have to move my face. Okay, so with our assumptions, the first one is that we randomly selected 61 kochia plants. Now I feel like I'm not spelling it right. You know what? Sorry, y'all. We randomly selected 61 plants in 2014 and randomly selected 51 plants in oh no, 52 plants, sorry y'all, I'm the type to backspace everything. 52 plants in 2017. The next one is that we can assume the results from 2014 have no influence on the results in 2017 of the plants resistant to the herbicide. You can add as much context as you want. No one will be upset by that. We can assume now, so that's our first case of independence. The next case is, since we are sampling, we have to assume we're sampling without replacement. So once we take a plant, we're pulling it out of the population. We're not putting it back in and then possibly randomly reselecting it. We've pulled it to be a part of our sample. So we're sampling without replacement. Therefore, we need to check the 10% condition. So we can assume there were at least 610 kochia plants. I feel like there's a hidden H in there. I just feel it in my soul. So we can assume there are at least 610 kochia plants in 2014 and at least 520 kochia plants in 2017. And we do this because when we sample without replacement, in order for the degree of dependence to be negligible amongst our observations, we have to make sure that we're sampling no more than 10% of the population. So I'm just taking my sample size and multiplying by 10 and saying I assume there's at least this many, because then I'm exactly at 10%. And by saying at least, there could be more kochia plants than the 610, but 61 compared to 610 is that 10% value that we're looking for. And then lastly, we have to check the normal model, but come on, it's an inference question on the AP exam. We can assume that it's going to work out. So the normal model is appropriate by large counts. And of course, I can't just claim this. I have to show the work here. So what I'm going to do now is I'm going to first move up my screen. So I'm going to take the first proportion here, which would be N14 times P hat 14. And notice that I no longer have the population parameter. I don't know for a fact that 19.7% of plants were resistant to this herbicide in 2014, but based on my sample, that's how many were. So I'm just going to plug and chug. So here we would have 61 times 0.197, and then we're also going to have this population size and its complement. So that'll be 61 times point something. I'm gonna just put a 0. See, look, we just go with the flow. And guess what? I forgot to write all these values down, so you are really getting the inside look. So here we get about 12.017, whereas here we get 0.803. And again, this is just a complement, so I could just take this away from 61 to find the remaining value. Well, look at that. Both values are greater than 10, but that's just for my first population. So now I also need to check my second population here. And here goes. Okay, so then in my other sample size, I had 52 times, looks like 0.385. And then the complement of that, so 0.615. All right, and when I do that, I get 31.98. And then we also get 52 times 0.385 is going to be about 20.02. And if we were to add these numbers, we should get our original sample size. So we notice that all of these are greater than or equal to 10. Therefore, the normal model is appropriate by large counts. Since all of our assumptions are met, we actually do have a procedure now that we can use to find a valid test statistic and a valid p-value, which is why we must assume normality. So we're going to say something like, since conditions are met, we will use a two-sample z-test for, not the fro, for the difference of population proportions. Okay, and now a little bit more work, because we assume that these two populations are equal. We actually now need to compute our test statistic here. So let's find a different color. Okay, so we need to note everything down. So here, p hat 14. Oh, nope, no. I've decided I don't want to do that. And we're going to go over some examples in class, so even if this video isn't precise, don't sue me. All right, so we need to compute the pooled test statistic, which is just our successes divided by the total sample size. So here I would take 19.7% of 61 plus 38.5% of 52. And I'm going to divide that by our sample size here, our total sample size, assuming these populations were equal. And when I compute this test statistic out, or not the statistic, but this sample proportion, I end up with the result of 0.2835, and then the complement there would just be 1 minus that, so that would give me, let's see here, 1 minus 0.2835, that'll give me a complement of 0.7165. Then our test statistic becomes z equals the proportion here. So since I'm assuming p17 is greater than p14, I'm actually going to rewrite this in a way that says p17 minus p14 all over the pooled test statistic and its complement times 1 over the sample size from 2014 and 1 over the sample size of 2017. And that's my terrible attempt at a square root there. We would just plug and chug all of these values into the calculator. We've already named the test once by formula and once by the name. So we're actually good to just give the z statistic here. And so that's going to be a 2.21 z value on our normal curve. And that's going to produce a p-value of approximately 0.0135. And again, I'll show you how these mechanics work in class. If you don't believe your calculator or me, you can go ahead and compute this out. But we've calculated our test statistic, we've obtained our p-value, we listed the parameters that we are testing, we've listed a set of hypotheses, we checked our assumptions, and we named the procedure. So last thing we need now is a conclusion that is in context. And we actually need two components for our conclusion here. We need a decision, what we're going to do, and then we need a decision, conclusion, decision. All right, so since, oh no, where did my typing go? Here we go. Since p-value equals 0.0135, and this is less than the alpha, which is equal to 0.05, we are actually going to reject the null. Which means, since we are rejecting the null, there is sufficient evidence to claim the proportion of kochia plants in 2017 that are resistant to herbicide G or glyphosate, yeah, I already forgot it. So you can either say, yes, there is sufficient evidence to claim there has been an increase, or you can just list off the context of the alternative hypothesis here, which is that there's sufficient evidence to claim the proportion of kochia plants in 2017 that are resistant to the herbicide is greater than the proportion in 2014 that was resistant to the herbicide. And again, this just, why can I not spell? Proportion that was resistant to herb G. And it looks like my face was covering up the p-value there. But essentially, we were just looking for evidence that would suggest that our sample didn't just happen by chance, right? We didn't just get lucky, but instead we have some convincing evidence that this is not a likely result. There actually is a difference in these proportions, and that's what the p-value is. Assuming that the proportions are equal, the probability of obtaining our result or larger is about 1.35%. And so that is a very rare value there, so we would call that statistically significant. Therefore, we have enough evidence to reject the null hypothesis in favor of the alternative. So again, we'll go over more of these examples and more of this process in class, but this is just a little insight into an FRQ style question for the difference of population proportions.